In this lecture, we are going to discuss about the numerical Part-2. Now, let me take the first numerical. The power input is 500 volts 50 hertz 6 volts 3-phase squirrel cage induction motor running at 975 rpm is 40 kilowatt. The stator losses are 1 kilowatt. The fraction windage losses is 2 kilowatt. Calculate the speed. So whenever we are going to calculate the speed, we should know the synchronous speed as well as the actual speed of the motor. So the synchronous speed ns equal to 120 FFT. Substitute all the values, we are getting 1000 RPM. The actual speed of a motor is given 975 RPM. So slipper induction motor equal to ns minus n by ns. So finally, we are getting the 0.025. Rotor copper loss. So here, the power input to the stator of induction motor is given, that is 40 kilowatt. The stator loss also given 1 kilowatt. The stator output power equal to 40 minus 1. We are getting the 39 kilowatt. The stator output power equal to rotor input power, because there is no power is wasted in a air gap of a induction motor. So the rotor copper loss equal to rotor input into slip of the induction motor, that is 39 into 0.025, we are getting a 0.975 kilowatt. The mechanical power developed in an induction motor, that is equal to rotor input power minus rotor copper loss, is getting the 39 minus 0.975 kilowatt, we are getting the 38.025 kilowatt. So whenever you're going to find out the British horsepower, you should know the how much power is available at the shaft. So the shaft power equal to the mechanical power developed minus individual fractional losses. We're getting the 38.025 minus 2. We're getting the 36.025 kilowatt. This divided by the 0.735, that is gives the 49 HP. This is not kilowatt, HP. Efficiency of a motor. The efficiency of the motor is defined as a ratio between output power to the input power. As about shaft power divided by the motor input power. Already we know the shaft power, that is 36.025 divided by 40. We are getting the 90.0962 percent. A 100 kilowatt, 3.3 kV, 50 head, 3-phase star connected induction motor has a synchronous speed of 500 rpm. The full load slip is 1.8%. The full load power factor is 0.8 lagging. The stator copper loss are given as 2400 watts. The iron loss are given 3500 watts. The rotational loss are given 1200 watts. Calculate the rotor copper loss. This is the rating of the motor, nothing but which is representing the output power of a motor. 100 kilowatt is nothing but output power of motor. The motor output power equals 100 kilowatt. The synchronous speed of a motor is given 500 rpm. The line voltage is given 3.3 kilovolt. That we can write it as a 3300 volts. The power factor of an induction motor to full load also given 0.85 lag. The full load slip of induction motor is given 1.8%. That we can write it as a 0.018. Stator iron loss is given, that is the 3500 watts, that we can write it as a 35 kilowatt. The rotation losses is given 1200 watts, that we can write it as a 1.2 kilowatt. Mechanical power developed in an induction motor, that is equal to output power plus rotation losses. These two values are given in the numerator. Substitute those two values, we are getting the 101.2 kilowatt. Input power equal to mechanical power developed by 1 minus S. Substitute all the values, we are getting the 103.055 kilowatt. The rotor copper loss equal to rotor input power into slip of the induction motor. Substitute all the values, you are getting the 1.855 kilowatt. Line current. Now here we know the rotor input power. The rotor input power equal to stator output power, because there is no power is wasted in air gap of induction motor. So the rotor input power plus stator copper loss is equal to the motor input power. Substitute all the values, you are getting the 108.955 kilowatt. Stator losses are nothing but stator copper loss and stator core loss also. So motor input power equal to root 3 VL IL cos pi equal to this value 108.95 into 10 to the power of 6. Line voltage is given. Now we have to find out the line current. The power factor of induction motor also given at full load. Substitute all the values and simplify this expression. You are getting the line current IL equal to 22.43 amperes. Nothing but in the induction motor is taking a current at full load 22.43 amperes of current. Full load efficiency. The efficiency of induction motor is defined as the ratio between the power available at a shaft to the input power taken by the induction motor. So the output power by input power into 100, we are getting the 100 by 108.9 into 100, we are getting the 91.2%. Now we're going to solve the one more numerical. A 76 kilowatt 3-phase 50 Hz 16-pole induction motor has a rotor impedance of 0.02 plus J 0.15 ohm at a standstill condition. Full load torque is obtained at a 360 rpm. Calculate the ratio of maximum to the full load torque. See, this is the value which is given for the rotor at a standstill condition. This is nothing but a resistance at a standstill condition. This value is nothing but a rotor reactance at a standstill condition. So synchronous speed ns equal to 120 f per p. Substitute all the values, you are getting the 375 rpm because the number of poles is very high, that is 16 rpm, so that the synchronous speed will be decreasing. The full load speed of an induction motor is given, that is a 360 rpm, that is given in the problem. So you take up the same value, 360 rpm. The full load slip equal to ns minus n by ns, that is equal to 375 minus 360 by 375. We are getting the 0.04. For the slip at maximum torque, that is equal to Sm equal to R2 by X2, that is equal to 0.02 by 0.15. We are getting the value 0.135. Now we know the slip of the induction motor at a maximum torque and slip of the induction motor at full load. Already we know the relation between the maximum torque to the full load torque in induction motor, that is equal to SFL square plus Sm square divided by 2 Sm SFL. Substitute all the values, you are getting the 1.81. This is representing the maximum torque in induction motor is more than the full load torque in induction motor. Speed for the maximum torque. So already we calculated slip at a maximum torque. So the speed corresponding to the maximum torque Nm equal to Ns into 1 minus Sm. Substitute all the values, we are getting the T25 rpm. The rotor resistance to added to get the maximum starting torque. Generally, the induction motor is designed for the low resistance for the rotor resistance and high reactance. The condition for the maximum torque is R2 equal to Sx2. So now we want to get the maximum torque at the starting. So the slip of the induction motor equal to 1. To substitute this value here, getting the R2 equal to X. R2 is nothing but a per phase rotor resistance. This value is always less than X. So we have to add the external resistance into the rotor circuit, so that the resultant resistance value equal to the. That's why here we have taken the R2 plus small r equal to X2. Now we are going to find out the small r. Small r is nothing but a external resistance per phase we are added into the rotor circuit, that is equal to X2 minus capital R2. Substitute all the values, you are getting the 0.13 ohm. So thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that always welcome to answer all your questions.